Hello, welcome to the course on analog and digital communication. Dear students, in the last class we have started digital communication, and in that lecture we have briefly discussed basic block diagram of communication, digital communication system. Okay, we have also discussed about the key process in digital communication, which is the sampling process. So what is exactly sampling process? So sampling process convert continuous time signal into discrete time signal. So this will convert continuous time signal to discrete time signal, or you can say that the sampling process discretizes the signal in time domain. Okay, so how to achieve this sampling, or how to sample the signal? So if you would like to sample continuous time analog signal, then we have to multiply the continuous time signal with periodic signal sequence, which is nothing but impulse train. So this is the impulse train. So if you multiply our continuous time signal with the impulse train, then the output of this process is the sampled output signal or discrete time signal So one of important thing that we have to keep in mind, that when we are sampling the signal, at that time the sampling frequency, that is the frequency at which we are sampling the signal, must be greater or equal to the twice of the maximum signal frequency. Okay, so and this is the nothing but sampling theorem. This represents the sampling theorem. This represents sampling theorem. Okay, so while sampling, this rate should be, or this condition should be satisfied. So we have discussed three different cases for this. That is, if we sample the signal at the frequency greater than twice FM, that is the oversampling, then there is no distortion in the signal. If we sample the signal at the frequency fs is equal to twice FM, which is known as a perfect sampling, then also there is no distortion in the signal. Correct? And this condition is basically known as a Nyquist rate. Fs is equal to twice FM is basically known as a Nyquist rate. Okay, that we mentioned in the last class. Okay, and if we sample the signal below the twice FM, that is known as undersampling, and in undersampling there is a overlapping among the adjacent samples. The adjacent sample gets overlapped, and due to that there is a loss of information, and this distortion due to the undersampling is basically known as a aliasing effect. That is known as a aliasing effect. Okay, and in order to correct this problem, in order to remove this problem, aliasing effect, we have to sample the signal at this rate, that is fs greater than twice FM. Okay, so this thing we discussed in the last class. Now today we are going to discuss the types of sampling, sampling techniques, or what are the different techniques by use of which we can sample our continuous time signal. So basically there are three types of sampling. One is the impulse sampling, second is natural sampling, and third is flat top sampling. So we are going to discuss all of these three in today's class. So let's start with the impulse sampling. So impulse sampling we already discussed in the last class. So basically नाम से पता चलता है, impulse मतलब we are using the train of impulse in order to sample the signal. It means our continuous time signal, that is x of t, is multiplied with the impulse train. Okay, impulse train. Okay, and you already learn about this impulse in your signal system course. What is the impulse signal? So sequence of the impulse, that is the impulse train, it gets multiplied with the continuous time signal, and output of this process is basically sampled signal. Okay, so if we write this thing mathematically, so suppose I have continuous time signal x of t and we are multiplying that with the impulse train of period t. Okay, then amplitude of impulse will change with respect to amplitude of the original signal x of t. तो आप देख सकते हो कि ये मेरा कंटिन्यूस टाइम सिग्नल है x ऑफ t, उसको हमने इम्पल्स ट्रेन के साथ मल्टीप्लाई किया, ये इम्पल्स ट्रेन है. देन रिजल्ट इज द एम्पलीट्यूड ऑफ इम्पल्स इज चेंज्ड अकॉर्डिंग टू एम्पलीट्यूड ऑफ द इनपुट सिग्नल x of t. So mathematically I can represent this impulse train by use of this relation, that is impulse train can be given as n is summation n is equal to minus infinity to infinity delta t minus nt. तो आप देख सकते हो कि impulse train which is centered at, this is centered at 0, this is impulse at ts, this impulse at 2ts, 3ts and so on. Similarly minus ts, minus 2s, 3s. It means the impulse train consists of impulse at time instant ts, 2ts, 3ts and so on according to this relation. Okay, and if I multiply it, then the resultant signal can be given as sigma n is equal to minus infinity to infinity x of nt delta t minus nt. This is my sampled signal. Okay, so this is our impulse sampling, and if you would like to get the spectrum of this sampled signal, then we have to take the Fourier transform of this equation or Fourier transform of this signal y of t. Then if we take the Fourier transform, then the spectrum will be given as y of omega is equal to 1 over capital T summation n is equal to minus infinity to infinity x of omega minus n omega s. Okay, clear? And this type of sampling, which is impulse sampling, is also known as the ideal sampling process. It is also termed as ideal sampling. It is also termed as ideal sampling process. Okay, or impulse sampling. And one of the important thing to note over here, this type of sampling does not use in the practice because the impulse cannot be generated practically. We cannot have the pulse with width approaches to 0. मतलब जीरो width वाला कोई भी pulse हमारे पास practically हम generate नहीं कर सकते. Okay, so generation of impulse train is not possible practically. If we cannot generate impulse train, then we cannot do or we cannot achieve impulse sampling. Clear है? So impulse sampling में कुछ नहीं है, सिर्फ हमें याद रखना है कि हमारा ओरिजिनल सिग्नल को हमें impulse train के साथ मल्टीप्लाई करना है, and in this process the amplitude of impulse will be changed according to original signal x of t. Okay, now next type of sampling is natural sampling. So natural sampling, so instead of using, as we mentioned that in impulse sampling we have to use the impulse train and we cannot generate impulse train practically. So one of the practical method for achieving sampling is natural sampling, in which instead of impulse we have the pulse train of finite duration, pulse train of finite duration or finite period t. Okay, so here you can see this impulse train is replaced by pulse train. Each pulse has a finite period t. Okay, so if we multiply our original signal x of t with the pulse train of period t, then the amplitude of this pulse train or amplitude of this pulse will be get modified, or it will get changed according to amplitude of the original signal x of t. So you can see this is our pulse train of period t, and if you multiply it with this original signal x of t, then the amplitude of this pulse train will change according to modulating or original signal, according to original signal. Okay, you can see. Okay, and impulse train is mathematically denoted as summation by this series summation n is equal to minus infinity to infinity p t minus nt. Okay, so output of this natural sampling is given as y of t is equal to original signal x of t multiplied by the pulse train. Okay, so the only difference between the impulse sampling and natural sampling is that we have replaced this impulse train by pulse train of period t. Okay, so that is written as x of t multiplied by p of t, and as I mentioned, p of t can be given by this series, that is sigma n is equal to minus infinity to infinity pulse p t minus nt. Okay, and if we represent the exponential Fourier series representation of pt, okay, this pt, then it can be given as pt is given as summation n is equal to minus infinity to infinity 1 over t p of n omega s e raised to j n omega s t. Okay, so it can be written as 1 over t sigma n is equal to minus infinity to infinity p of n omega s into e raised to j n omega s t. Okay, and if we substitute this p of t in this equation, okay, then we will get, in this equation, instead of p of t, if we put this value, okay, then we will get x of t is multiplied by 1 over capital T summation n is equal to minus infinity to infinity p of n omega s e raised to j n omega s t, and this would be, if we take it inside, then y of t output is given as 1 over capital T summation n is equal to minus infinity to infinity p n omega s x of t e raised to j n omega s t. Correct? Okay, and if you would like to represent the frequency domain representation of this signal, then we have to take the Fourier transform of the same. If we take the Fourier transform of this signal, then we will get the frequency spectrum or spectrum of the sampled signal. Now third type of sampling, which is the flat top sampling. So whenever we are transmitting the signal, the noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in form of the flat top. मतलब जो हमने पल्स ट्रेन है उसको, मतलब जो नॉइस इंट्रोड्यूस होता है, तो अगर उसमें नॉइस को हमें इजीली रिमूव करना है, तो अगर ये पल्स ट्रेन है वो, जो हमारा जो सिग्नल है सैंपल सिग्नल, वो फ्लैट टॉप होगा. फ्लैट टॉप, उसका जो टॉप, मतलब जो पल्स का जो टॉप है वो फ्लैट होगा, देन वी कैन इजीली रिमूव दी नॉइस फ्रॉम द सिग्नल, वेरी इजी. ओके, तो अगर ये सैंपल सिग्नल को आप इसके साथ कंपेयर करेंगे तो आप देख सकते हो यहाँ पे जो सैंपल्स था उसका जो टॉप है वो फ्लैट नहीं है. ओके, वो फ्लैट नहीं है. दैट कैन बी वेरीड अकॉर्डिंग टू द ओरिजिनल सिग्नल. ओके, बट इन फ्लैट टॉप सैम्पलिंग, ड्यू टू द प्रॉब्लम ऑफ नॉइस, if you would like to remove the noise easily, then the pulse should be, the top of the pulse should be flat. The top of the pulse should be flat. So here in this case, the top of the samples are flat. It means they have the constant amplitude. Okay, hence it is known as a flat top sampling or practical sampling. Okay, and very important, flat top sampling make use of sample and hold circuit. आप देख सकते हो कि यहाँ पे जो सैंपल सिग्नल मिल रहा है उसके जो पल्स है उसका टॉप फ्लैट है. दैट इज ओनली डिफरेंस बिटवीन दी फ्लैट टॉप सैम्पलिंग एंड नेचुरल सैम्पलिंग. ओके, सो द आउटपुट ऑफ द फ्लैट टॉप सैम्पलिंग कैन बी गिवन एज y of t is equal to p of t multiplied by y delta of t. Okay, so y delta of t, that is our ideally sampled signal. ओके, दिस इज अवर आइडियल सैंपल सिग्नल. मतलब आपको आपका जो सिग्नल है उसको आइडियल सैंपल सिग्नल है, दैट इज y ऑफ डेल्टा टी, दैट इज मल्टीप्लाइड बाय द पल्स ऑफ पीरियड t. तो आप देख सकते हो ये p ऑफ t मेरा एक पल्स है. ओके, इसका जो पीरियड है, टाइम पीरियड है, वो कैपिटल T. ओके, एंड दैट इज गेट्स मल्टीप्लाइड बाय विद द आइडियली सैंपल सिग्नल. ओके, इम्पल्स सैंपल सिग्नल, एंड आउटपुट इज द flat top sample signal. So the theoretically, this is theoretically, because this cannot be generated practically. correct? Ideal sample signal cannot be generated practically. So theoretically, flat top sampling can be achieved by multiplying this ideally sample signal with the pulse of duration t. Okay, so and output is the flat top sample signal, that is y of t. Okay, so the sample signal basically obtained by convolution of the rectangular pulse p of t with the ideally sample signal y of delta t. Okay, so this is y of delta t basically. Okay, so if we convolve these two, then output would be sample signal, flat top sample signal. So that can be written as the output signal y of t is nothing but convolution of pulse, not pulse train, that is pulse of duration t, convolve with ideally sampled signal, that is y of delta t. Okay, so the flat top sample signal is given as convolution of pulse of duration t of period t convolve with the ideally sample signal, that is y of delta t. And if you would like to get the spectrum of the sample signal, then this convolution will be converted into the multiplication in frequency domain that we know according to the property of the Fourier transform. So if we take the Fourier transform of this signal, if we take Fourier transform of this time domain signal, that is output of the flat top sampling, then we will get the spectrum of the sample signal, and in that case the convolution will be converted into multiplication. Okay, so it is given as y of omega is equal to p of omega into y of delta omega. P of omega, that is the spectrum of this pulse, and y of delta omega is the spectrum of this ideally sampled signal. Okay, so this is the flat top sampling process. So आज के लेक्चर में हमने क्या डिस्कस किया? सो इन टुडेज क्लास वी हैव बेसिकली डिस्कस अबाउट दी 3 डिफरेंट टाइप्स ऑफ सैम्पलिंग प्रोसेस. One is the natural sampling, first is the impulse sampling, second is the natural sampling, and third is the flat top sampling. So I hope कि आज के लेक्चर में जो हमने डिफरेंट टाइप्स ऑफ सैम्पलिंग डिस्कस किए वो आपको समझ में आ गया होगा. Let's stop here. We'll continue with the other aspect of this course in our next video lecture. Thank you very much.